So on Wednesday, we talked about an exhaustion proof. There are a finite number of cases. Let's just go through each of them, because a universally quantified statement is really a giant and statement. But sometimes I want to do this idea even when there are an infinite number of options. If I can find a convenient way to subdivide my infinite set. An example. If you have two numbers and you take the smaller one and add it to the larger one, you get the same thing as if you just added the two numbers together. Now, when you say it like that, it kind of makes sense. One of the numbers is smaller, one of the numbers is bigger. Take the small one, add it to the large one. That should work. But if I want to prove this, I should, in some sense, know which one of these numbers is bigger and which one is smaller. So instead of trying to do this as a single general statement, I'm going to look at the options. Which of these two numbers, x or y, is smaller? Which is bigger? So I'm going to do this by cases. And my three cases, well, let's start with the easy part. Case one, x is smaller. Okay, well, if x is smaller, then when I look at this up here, the minimum of my two numbers is x, and then the maximum of my two numbers is the other one. And therefore, the minimum plus the maximum is exactly what I wanted. But that's not the only option, is it? I could have the other option, that x is the bigger number. Well, now, the minimum of my two numbers and the maximum of my two numbers switch places. And then, when I do minimum of the two plus the maximum of the two, what do I get? Careful, because what I actually get is y plus x, but I know that the order in which I add doesn't matter, so that's the same as x plus y, which means I got what I wanted. I'm being pedantic here, Blake, and I'm really going to say, no, I've got to write it down the way it's set up, and then we'll fix it to make it match. And now I'm like, good, I did all the cases. You're shaking your head, Gracie. What did I miss? Yeah, that's not up there, is it? It is a valid option. The two numbers could be the same. So what happens when I go to do case 3? Well, here's the best part. If I ask you which of these two numbers is smaller, it doesn't matter which one you pick, does it? Which is smaller, 3 or 3? Well, 3 is smaller. Which 3? The first 3 or the second 3? Does it matter? No. So I could say, well, these are actually the same. It doesn't really matter which one I pick. Same thing for the maximum. So now when I go to add the numbers, I'll pick which one I want, right? So I'll pick this one and I'll pick this one. And then when I add the minimum and the maximum, I get x plus y. By the way, if you hadn't chosen the two things I circled, let's say you chose y both times, then you'd write here, you'd write y plus y, wouldn't you? But then you know that x is equal to y, so you can replace the first y by an x. It's still going to work out to be x plus y. Ta-da! Insert little box, QED, etc. here. I did it. If a proof by exhaustion would not work, clearly it won't work here. X and Y can be any two real numbers, and there are infinitely many of them. I can't do all of them individually. Or there's no necessarily clear path to what I should do for a direct proof in just one step. Maybe this sort of subdivision helps. It's certainly not a bad starting point. Questions? I am inherently a lazy human being. My goal is to write the shortest, most concise, smallest argument I can write. And when I look at this, I look back at proof cases 1 and 2, and I say to myself, didn't I really do the same thing? I just changed the name. Which one was bigger, which one was smaller? If you switched these letters here, you'd switch these letters here and these letters here, and you get exactly what we wrote right here. So if I tell you I've got two numbers, and one of them is bigger and one of them is smaller, maybe I can change this setup and only do it once. The only thing I know about cases 1 and 2 is there's one thing that's not allowed. What's the one thing that is not covered in either case 1 or case 2? They're equal. So I'm going to call this case 1.5. They're not equal. Suppose x is different from y. If they're different, then one of them is smaller and one of them is bigger. I am now giving you the privilege of assigning names to my values. I have two numbers. I know they're different. This is the smaller one. What do you want to call it? X or Y? It's your choice, isn't it? If you call the smaller one X, then you're doing this. If you call the smaller one Y, then you're doing this. But they're really the same argument. You just have to know which one is the smaller one. I'm going to take this privilege for my own. It is irrelevant to the argument I'm going to do as to which one I call which letter. So I'm going to now say, without loss of generality. In other words, it doesn't affect how specific or general this argument is. I'm going to let X be the small one and Y be the big one. I could just as easily have said, without loss of generality, Y is the small one and X is the big one. It doesn't matter. It's my call. I have one big one and one small one. Here's my big number. Here's my small number. I'm going to call this one X and this one Y. Now I go through the exact same argument. Then the minimum is X and the maximum is Y. So minimum plus maximum is x plus y. And I only have to write that down once. I don't have to do, well, what if the other way? It doesn't matter. Just change the names of the numbers. I forgot to bring my props. I have two little buckets labeled minimum and maximum in my office. They're foam cups from the cafeteria. Well, which one is which? I don't care. It's there. Which one's X, which one's Y? Just call the label on which box you want. Advantage. My choice is then got to be consistent through the rest of the proof. We did this all the time in calculus. What am I going to call this function? F of X. Why? Because it's a convenient name. You could have called it Henry. I don't care. A list of examples is not a proof unless that list is exhaustive. There are a lot of results today that we have huge lists for. X, Y, Z, and N are all integers. X, Y, and Z can be positive or negative or zero. Not zero. Wait a minute. I should write that down. Non-zero integers. If you let N be a number bigger than 2, this has no solutions. Up until recently, this was a conjecture. This was written in the margin of a book called Discussions de Arithmetique, which I believe the original's in Greek, but it was translated in French, was owned by a guy by the name of Pierre de Fermat. And he made this note in the margin. And in the margin, underneath this, he wrote, I have a lovely proof of this. It's too small to fit in the margin. There's just one problem. The word he used in French wasn't the word proof. It was the word demonstration. And he could demonstrate this. He had a list of examples. A huge list of examples. This particular copy of arithmetic had lots of notes like that in the margin that Fermat wrote. All of them had been proved except this one. So it became known as Fermat's last theorem. Now, dozens of people had been working on a proof of this for years and years and years, to the point where people actually would not just work on this particular proof, but they would try and work on small slices of it. What if I only look at n being 4 or 3 or even, or if I know some relationship between x, y, and z? Hundreds of people. People started stocking away money. If you solve this one, if you prove it, I'll give you a prize. The Danish king offered 50 gold kroner, 1830. By the way, 10 years ago, that was worth 300,000 kroner. Interest is a wonderful thing. Andrew Wiles wrote a proof of this. Spent, I wish I was kidding, 7.5 years working on this. Walked into a conference and gave a talk, I love the title, on rational points of elliptic modular curves. I know what each and every one of those words mean on their own. I have no idea what they mean together. And he gives this talk, and there are like 5 people in the room. And he hands out the paper and he says, I'm going to give some today and some tomorrow and some the next day. And on the second day, there were about 20 people. And on the third day, the room was standing room only. There were hundreds of people in the room. And the very last thing he wrote, and because of this is true. And he'd written a proof of Fermat's last theorem. They sent it off to a whole bunch of other mathematicians going, please critique this. Tell me if it's right. And somebody said, on page 73, there's a hole. You're using the Taniyama-Shimura conjecture, and we don't think you have this connection right. 2.5 years later, he fixed it. He won the prize. That's less than a decade old. 250 years to get to this proof. But we started with list after list after list of examples. A list of examples is not an exhaustive proof, because that's an infinite collection of numbers. Okay. By the way, they made a movie and a book about this, about Weil's proof. It's called The Proof, because it was the big one everybody was waiting for. Questions? All of the things I've been talking about are universally quantified statements. For all x, for all y, for all z. For x and y, any real numbers. What about existence proofs? If I just want to show there exists a number for which some property is true, there are actually two different ways to do this. I could simply find the number, or the x, or the whatever it is. Constructive proof. Find the x. Here is an existence claim. There is some positive integer that can be written as the sum of two cubes in two distinct ways. Do you know what this number is? But you could start checking, right? You could look at the number 1. Well, 1 is 1 cubed. 1 cubed is 0 cubed. But that's the only way to do it. 2 can't be written as the sum of cubes. 3, 4, you could keep going, right? I'd be here for a long time. By the way, the answer is 1,729, because that is 12 cubed plus 1 cubed. It is also 10 cubed plus 9 cubed. I didn't come up with this on my own. Again, there's an apocryphal story here. The Indian mathematician, I'm going to screw this guy's name up, Srivanesan Ramanujan, was brought to England by G. Hardy, and Hardy went to visit him when he took ill. And he walks in to Ramanujan's sick room where he is, man, this guy does not look good. So Hardy is trying to figure out how to start a conversation. And he walks into Ramanujan's room and says to Ramanujan, I'm terribly sorry, I took the most boring cab over. It was cab number 1729. Ramanujan, without opening his eyes, said, no, that's the smallest number that can be written as the sum of two cubes in two ways. Ramanujan wrote notebook after notebook after notebook of ideas in number theory, claimed he was inspired by the gods. Every single thing we've taken out of his notebook so far has been proved true. He didn't write one proof. I don't know how he came to them. There's a really good movie on this one too. Ramanujan is a great movie. Now, the problem is, if I want to solve this, how do I show that this is the smallest number that works this way? I have to show you can't do it from 1 to 1,728. Bleh. But it is possible to write non-constructive proofs. By the way, this particular problem I can do both ways. I can do this by constructive proof, or I can do this by non-constructive proof. Oh, I wrote 1,000. That should be 100, not 1,000. Excuse me. I can do it for 1,000. I just haven't done that one yet. So, would you like me to start with the constructive or the non-constructive? Constructive. Start there. Grab your calculators. Square root of 6,401 is not an integer. Right? 6,401. Take the square root. You don't get a whole number. I've built you a list of 100 numbers. I don't care which one you pick in the middle there. Any number between 6,401 and 6,500. Take the square root. You will not get a whole number. Blake, which one did you pick?
64, 64.
64, 64. The square root is 80.399.
399.
Right? Point something. It's not a whole number. Now, the obvious answer to this is, how the did you figure this out? Here's a non-constructive proof. If I want none of these numbers to be perfect squares, then all of my numbers have to be between n squared and n plus 1 squared. Yes? If all of my values are between these, then none are perfect squares. There are no squares between 2 squared and 3 squared. There are no squares between 5 squared and 6 squared. There are no squares between n squared and n plus 1 squared, right? N plus 1 squared is n squared plus 2n plus 1. Yes? How many numbers are between these two? Oh, that would be the difference, right? So if I take n plus 1 squared minus n squared, that tells me how many things are in the middle. But that's n squared plus 2n plus 1 minus n squared. That's 2n plus 1. If I want 100 numbers that are not squares, I need 2n plus 1 to be bigger than 100. Which means 2n bigger than 99, n bigger than 49.5. Pick any number larger than 50. Start your list there. 50 squared. 50 squared is 2,500. What's 51 squared?
26,700.
There are 101 numbers. I have to have a list of 100 in between, don't I? By the way, 6,400 is 80 squared, so I just picked a number that I knew was bigger than 50. I did not construct the list here, did I? Yet I still showed you that such a list must exist. A non-constructive proof that still shows the existence of an item. I like constructive proofs a whole lot. There's something that does it. See this one. But I don't need a constructive proof. The intermediate value theorem. If my y value is negative here and positive here, it had to go through 0 somewhere in the middle. I don't know where in the middle, but that's an existence proof. It doesn't build me the root. It just shows me one has to be there. Ta-da! Questions? Sometimes I don't want to know that there is such a thing. I want to know that there is one and only one such thing, right? A uniqueness proof in addition to an existence proof. A uniqueness proof almost always starts with an existence. But if we think about it, because that makes sense when we were talking about uniqueness, weren't we really doing that? That's an existence and more. And what we would do is we would say, oh, there exists x, p of x, and if I pick a y that's different, then not p of y. Which, by the way, we would almost always prove using contraposition. So you show, hey, there's this number that works. And if it was something else, then it would be the same as this one. So a uniqueness proof is an existence proof. And then we add more. There are a lot of uniqueness proofs in higher analysis. There aren't that many of them at this level. If a and b are odd integers, then there is an integer c. I didn't write that down. I wrote down there exists a c. I should say c is an integer. where C is the same distance from A as it is from B. Intuitively, pick two odd numbers. Let's do an example or two before we say whether or not we think this works. Pick two odd numbers.
9 and 7.
9 and 7? Isn't 8? The absolute value of 8 minus 9 is 1. The absolute value of 8 minus 7 is 1. Two other odd numbers.
15 and 13.
14, right? One from each of them. Make them further apart. 73 and 31. 52. What's 73 minus 52? 21. What's 52 minus 31? 21. All right, wait a minute. How the hell did I pull 52 out of thin air? I think of these as distances. I'm on a number line. I have A and B. They're both odd numbers. I want that number in absolute value to match that number in absolute value. Where is that point C? Geometrically. It's the middle. So it's the average of the two, isn't it? Hey, okay, let's see if we can prove this. Proof. Suppose A and B are odd integers. Then, wait a minute, what's it mean to be odd? Okay, but I got two different integers, so they might be two times different things, right? So then there exists K1 and K2 integers with A equal 2K1 plus 1 and B equal 2K2 plus 2. By the way, if you don't like K1 and K2, use any other letters you want. Just don't use A, B, or C, because those are already something here. So let's think about our midpoint. I've constructed it. This is a constructive idea. Let's see if this works. If C is A plus B over 2, first I need to know that C is an integer. Is this an integer? Well, that's 2K1 plus 1 plus 2K2 plus 1 all over 2. Wait a minute. I have a plus 1 and another plus 1. What happens when I do that division? And those are integers, right? K1 is an integer, K2 is an integer, 1 is an integer, and when you add integers, you get an integer. Integer. Now I need to know that A satisfies my property. What is the absolute value of A minus C? Well, that's A minus A plus B over 2. I need to add fractions, subtract fractions. I need a common denominator, don't I? So that's going to be 2A minus parentheses A plus B over 2, A minus A, so that's A minus B over 2, right? With me so far? Now let's do B minus C. So that's B minus A plus B over 2. Same thing, 2b minus parentheses a plus b all over 2. What do I get? What do you know about those two things? Because a minus b is minus the quantity b minus a, isn't it? And that means that the absolute value of a minus b is the same as the absolute value of b minus a. Those two are the same. Okay, I proved there is a number. But I'm not done. Because what was I actually trying to show? I was trying to show there's only one. So now I showed it exists. Now for the uniqueness part. So let's suppose we have a different one. Then we have two options because these are absolute values, right? They're either the same or one is the negative of the other. Yes? So case one, A minus D equals B minus D. Case two, A minus D is equal to D minus B. Those are the two cases. Hey, what happens in case one? Hey, wait a minute. If I have two numbers and they're equal, and I take the number in between them, what do I get? So that would mean that A and B and C are all the same. So isn't D the same as C? It's the number in the middle. It's the same thing. What about down here? If A minus D is the same as D minus B, well then I'm going to move the things that are negative to the other sides. So this is the same as saying that A plus B is equal to D plus D. What's D plus D? Shakespeare. 2D or not 2D. Lame jokes. Hey, wait a minute. That means that D is A plus B over 2. That's the same as C. There's only one number that does this, and that's the number C that we came up with already. If you try and do it with something else, you really got the same number. You just called it something different. Check mark. There exists one and only one number that does the job. Questions? A proof is like a trig identity. I know where I'm starting with this expression. I know where I want to end up. What's the road in the middle look like? You are Google Maps. Get to this place. You know all this shit. What's the road you're going to take? And that's what this is. It's a map of your argument. Problem is, you've got lots of different starting points, right? You've got lots of different base ideas. I started with the definition. What's it mean to be odd? And I worked from there. Sometimes it's worthwhile to start with our conclusion and say, what would cause this? Work backwards from that a little. Work from your hypothesis, work forwards, and see if you can meet in the middle. So some proofs, you're going to do a direct proof. Start with if P, then Q. Work backwards from Q and say, well, if I can get here, then I know I'm right. Now work forwards from P and see if you can get there. See if you can meet in the middle. You have to be careful, though. Remember our 1 equals 2 proof? 0 equals 1, the garbage that we did last time where there was a clear mistake. You have to be careful when you do that you don't accidentally make one of those kinds of mistakes. Sometimes it's worthwhile to look at a proof you've seen previously. In section 1.7 and sections 1.8, there are probably 30 to 40 different proofs. I don't want you to memorize these, but I want you to recognize that the same sort of thing is happening in most of them. I could ask you to prove this. And my first reaction would be, I don't know where to start with this. But didn't we do a proof about the square root of 2 being irrational? I'll bet we could adapt that, couldn't we? In the same vein, if I asked you to prove that the cube root of 2 is irrational, I'd probably be able to do the same thing and somehow adapt the proof I already know. So one of the important things to do in trying to do a proof is to look at what's already been proved that I already did and say, what can I do that's a similar argument? In some cases, particularly in calculus and analysis, which is what I am most familiar with, some proof techniques get used so often they end up with their own names. There's a very particular argument where instead of trying to show that these 2 points are arbitrarily close, you say, well, this one's arbitrarily close to this one, and this one's arbitrarily close to this one, and these 2 are close enough. So instead of doing it in 1 piece, you do it in 3 pieces. We're trying to show things are close enough. That's an epsilon. Remember epsilon and delta in calculus? That's called an epsilon over 3 argument. It's so common, you just write, oh, an epsilon over 3 argument works here, and everybody knows what you're going to do. You actually have to do the whole thing, provided it's right. There are lots of different ways to do proofs. Lots of problems are examined through these same lenses. A very famous mathematician by the name of Polya wrote a book called How to Solve It. Which isn't just about solving math problems, but it's about the way in which you approach a problem in general. And it applies to proofs, it applies to labs, it applies to coding, it applies to engineering, it applies to architecture. You just have to decide, how am I going to do this? What do I already know? What have I done that worked before? Can I adapt any of those things? This is not a deep, a thick book. Polya's book is only about 100 pages. It's a weekend read, and it's really quite deep. One of the more important things we do in conjectures, in proofs, is we look at things that we don't know whether they're true or not yet. I'm about to give you $1 million problem. Pick a number. If that number is odd, multiply by 3 and add 1. If the number you picked is even, divide by 2. Take the number you get out, do it again. Take the number you get out, do it again. Do it again. Do it again. Repeat this process. I claim the list of numbers you make eventually gets stuck in a loop. And that loop goes 4, 2, 1, back to 4. This is known as the Goldbach conjecture. Sorry, no, Lagarius's conjecture. Goldbach is later. It's more commonly known by this idea, 3x plus 1. There is an entire book on attempts to prove this. No one's found one yet. Jeff Lagarius online keeps this book. So if you Google 3x plus 1 conjecture, you'll find a link to his webpage. He's got thousands of different attempts to prove it, and lists and lists and lists of examples. It's still not a proof. Nobody knows. So one of the questions is there an easy way to think about this? A lot of people try and think about this problem in binary. Since you're dividing by 2 a whole bunch, right? If you're in binary, an even number is going to end in a 0, just throw the 0 off. If you don't know binary, we'll do it in chapter 4. So this process becomes easy to do in binary, which means it's easy to code. And that means I can run thousands and thousands of examples by letting the computer go at it. Prove every number eventually ends in this loop. Nobody knows. We already talked about what it meant for a number to be prime, right? A monk by the name of Marin Mersenne claimed that if you took P and raised it to a prime number, then you would get a prime. 2 is prime, so 2 squared minus 1, that's 3. That's prime. 3 is prime. 2 to the third minus 1, that's 7. It's also prime. 5 is prime. 2 to the fifth is 32. 32 minus 1 is 31. That's prime. So, unfortunately for Mersenne, it turns out that 2 to the 11th minus 1 is 2047, happens to be 23 times 89. So Mersenne was wrong. But finding this counterexample took quite a while. Because Mersenne did this, by the way, in the 1600s. The fastest calculator was this thing. Lots of open problems and open conjectures like this drive us to learn new techniques and new examples and new approaches. These are the questions, by the way. The 3x plus 1 conjecture happens to be related to a group of conjectures put forth by the Clay Math Institute. Again, I want you to Google something for me. Google the Millennium Problems. In 2000, they came up with a list of problems and they said, these problems are so important to developing new ideas in math that we will pay you $1 million if you can solve any of them. So far, 1 down, 6 to go. The guy who solved the one turned down the money. I think he's crazy, but he did. There's a lot of interesting stuff on the Clay Math website. Go look. I'll see you all later. Enjoy your weekend.